Morning, everyone. So today we're going to start into a new chapter. This is going to be Unit 9, and it's going to be a chapter on redox or electrochemistry. So this first little bit here, we'll just introduce some of the vocabulary that we're going to see in this chapter. First of all, what we're going to see here is this redox is actually two half reactions. The ox part here actually stands for an oxidation reaction. In the past, they used to define oxidation as, it's reactions that react with oxygen. If you don't have oxygen, it's not oxidation. Later on, they sort of qualified the definition a little more. They realized all oxidations had in general, we had a species that was actually losing electrons, or a species loses electrons. So it passes electrons. In general, that would just have free electrons in nature. Charges in general are unstable. Unless there's something that's willing to pick up these electrons, the first chemical wouldn't actually be oxidized. So that actually coupled up with the second part here. That's this red part. This red part here is for reduction. And essentially, we're going to have a species gains electrons. Right, so very similar to acid-base chapter, we're looking at one person donating and one person accepting. The difference would be this time we're talking about electrons that are actually being charged, that are actually being passed around. And it's not just going to be a one proton transfer, it can be any number of electrons. We'll talk about balancing of these half reactions in upcoming lessons. So those are the two key terms here. Throughout this chapter, we have a lot of corny acronyms, just for that you can remember this better here. One that people always remember here is if you say to yourself, Leo the lion says grrr, and then you're just going to shorthand that GER. Basically, that stands for here, the L, loss of electrons, is oxidation, while with the grrr, gain of electrons is reduction. We're going to qualify these terms a little bit more in this lesson here. It's a little bit strange for us to think about, well, reduction usually means something is dropping, and yet what I'm specifying here is we're actually gaining. Just turns out here the things that we're gaining are actually negatively charged. The thing that's actually being reduced is actually our charge, or in this lesson here, our oxidation state or oxidation number. So we'll just start off here. First thing you're going to want to do is be really comfortable identifying oxidation state, finding the oxidation state for a particular element. The oxidation state is basically charge an atom would have, assuming or if ionic. So this is basically a made-up charge. Especially if it's ionic, it's no problem. Like, let's say I have NaCl, and if I say, well, what's the charge of Na? You can say, well, Na is +1, or chloride. Chloride here is -1. Well, if I pretend this is ionic, well, it is ionic. Well, what's the charge of sodium? Well, sodium's oxidation state is now +1. Chloride's oxidation state is now -1, right? Really easy for an ionic compound here. This is where it really is important here. You have to put the sign first and then the number. So even on their mark scheme here, they actually mark you wrong if you put 1+ instead of +1. The only reason why I can think about why they might do this here, later on we're going to have oxidation states that are like fractional, so 8/3, things like that. I guess reading +8/3 is easier than reading 8/3+. But aside from that, you just want to do that convention here. It has to be the sign first, has to be the plus or minus first, and then the digit afterwards. For the longest time, oxidation number was just using this sort of way of writing it, using the digit here. Oxidation state they had reserved for Roman numerals. Lately, what they've done is they've just switched that a little bit, and they said oxidation number is using the Roman numeral. So in this case here, sodium. Usually when you see Roman numerals, it's for the multivalent metal. In this case here, that number there is actually the oxidation number. Nowadays, we just use the terminology oxidation state and oxidation number interchangeably. So they just indicate to you the charge if the thing is ionic. Now, of course, if this is ionic, well, why bother create a whole new term for this one here? Let's take a look at a slightly different compound. Let's say NaClO. So realistically here, sure, the Na is still a plus charge. The ClO is actually a covalently bonded compound. It's a polyatomic, overall having a charge. Between the charges, this is an ionic bond, right? Positive and negative attract ionically, and yet the Cl and the O are covalently bonded, they're electron sharing. What we're going to do in this section is we're going to say, let's pretend the whole thing is ionic. Let's forget about the fact that these guys here, non-metal, are actually, no one really transfers the electron. What if I were to assign charges to these guys here? And what we're going to do is we're going to come up with a list of rules here. These are totally made up charges. And basically, it'll show me, it's kind of like the chlorine is this charge. If I check what the chlorine is on the other side, I can check whether the thing has been oxidized or reduced. It's just an easy way for us to figure out whether we've gained or lost electrons. So in the rules that we're going to be going over here, alkalis would typically have a +1 charge, so not a problem there, +1. I know the ClO technically doesn't realistically have a charge, but if O were to have a charge, O in most compounds here is a -2. We're going to see a rule later on that if I add up all the charges, they have to give up the overall charge. In this case here, I have a +1 with chlorine minus the 2 from oxygen, actually give you a 0, a neutral molecule. So therefore, the chlorine now is in like a +1 charge. Does it really have a +1? No. But this is its oxidation state, just for easy tracking whether it's going to be oxidation or reduction. So, again, there's this list of rules here, just pretending things are ionic here. I'm going to use this set of rules here as a sort of backup here. I'm going to give you the rules that in the way that I learned it here. Both ways work. Doesn't matter which list you follow, but pretty much the more practice you get, the faster you'll be in doing this. So, let me just start off here. So in terms of these rules here in assigning charges, the order does matter here. So first one, anything that's elemental, so all elemental states, all elemental ones are given a charge of 0. So this is sort of a catch-all. If someone hands you a block of lithium, right? So lithium is a metal. It has, on average, every atom has 3 valence electrons. Everything likes being neutral. So this one here implies it's a lithium atom. If I said, what's the oxidation state of this one here? If you pretend this is ionic, well, what charge does it have? Well, it has no charge, 0. What about, let's say, xenon? Xenon is a noble gas. Again, 0. What about fluorine? Fluorine is a diatomic. Again, although it would become fluoride when it is in compound, this is the elemental form. This is the diatomic way of appearing. Both fluorine atoms, so I have an F and an F. We're going to see oxidation state is defined per atom. I'm going to say, well, since overall you're neutral, this F is 0 and this F is also 0. So pretty much everything that's elemental, I just assign it a charge of 0 and call it a day. Second step here, we're going to, if I have a very simple ion, just the one ion, I see its charge already, you're going to give its charge as the oxidation state. So for example, we have our lithium. When lithium becomes plus, it's no longer the neutral atom anymore. If I said, let's pretend this lithium here is an ionic compound, well, it is ionic. So this one here is a +1, again, sign first in the number. I asked you earlier with fluoride, so F minus. When it was in the F2 state, we had called the oxidation number 0, but now fluoride has actually stolen an electron from someone. This fluoride here is actually going to be in the -1 state, so on, so forth. So most elements here, depending on what compound it's actually in, the oxidation number might be different. Third rule here, probably most important. This rule will sort of come back again and again. If you sum up all your oxidation states, if you add up all these oxidation numbers for all the elements, they have to add up to the overall charge. Even though these ones here are sort of fake charges here, we do want to make sure that we don't suddenly have more electrons than we do or less electrons. So earlier I had given you the compound. Let's just do it again. So NaClO. Normally in an ionic compound, you'd say, well, Na has a plus, ClO has a minus. I've already worked out so the cation actually cancels the anion. What I'm saying now is I'm saying, well, this one here is a neutral molecule. This one here has an overall charge of 0. It's counterbalanced. So whatever charge that sodium has, plus whatever charge that chlorine has, plus the oxygen has to add up to the 0. We had decided sodium was a +1. Chlorine, I didn't know. I don't actually have any rules for it. It's oxygen that I have a rule. Oxygen is usually going to be -2, so therefore chlorine has to be +1, so that when you add up all those ones there, it actually adds up to the overall charge. Let's try another one here. Let's do MnO4 minus. Right, it's permanganate. Okay, so it's a polyatomic. Realistically, it's covalently bonded. We're just going to say, let's pretend it's ionic. If it were ionic, again, oxygen is usually the one that's a -2 charge. I have 4 of them, so that would end up giving me a -8 overall. Whatever manganese has, minus the 8 from oxygen, has to leave you with the overall charge of -1. You should be able to say to me manganese is a +7 oxidation state. Again, just because you found manganese in this compound here doesn't mean now memorize manganese is always +7. Manganese is one of those transition metals we would expect, depending on the compound that's in, it may actually have a variable oxidation state. So if most elements here, you're going to test compound by compound, which are the ones that we can sort of bank on? We've already been starting to use this one here. Pretty much if we have an alkali metals are typically given a +1, so not their neutral, not their atom state, but when they become charged, +1. Hydrogen, we also typically call it +1. We're going to see a few exceptions here or there. And the other one here is oxygen, which appears in a lot of these compounds. Well, that's why oxidation they thought for the longest time it had to do with oxygen. Oxygen is usually going to be a -2 charge. The thing here is, when I list for you the rules in this fashion here, if any of these later rules sort of contradict one of the earlier rules, I want you to keep the early rule. So for example here, everything was good up to now. We said alkali was +1, oxygen was -2. We were able to find the charges. That's perfect. What if I have an example of a hydride? So this is a sort of an exception here. A hydride actually has hydrogen actually acting as a nonmetal. Hydrogen is sort of split personality here. It can either gain 1 electron or lose 1 electron here. So I have this compound. Let's check my rules here. Is it the elemental state? Well, no, it's bonded. Is it a simple ion? No, I don't see the charges. The sum of the oxidation states here have to add up to the overall charge. So whatever sodium has plus whatever hydrogen is has to give me the overall charge. If it's a molecule here, the overall charge is neutral, it's 0. Then we start following the rules here. Okay, alkalis are +1, hydrogen is +1. What's wrong with this? Well, if I follow the rules just sort of to the letter, the +1 and +1 will give me a +2, and that doesn't actually give me the overall charge of 0. Because this sum of oxidation state rule came first, I'm going to actually start just sort of following the rules in order here. All right, so I know they have to add up to 0. That's more important. The alkali is given +1. Sure, hydrogen is weird in this compound here. What would hydrogen have to be so that they would actually add up to give 0? So in a metal hydride here, hydrogen actually switches over to a -1. For most compounds, hydrogen is going to be +1, no problem. We're going to practice that quite a lot, but just don't be surprised. Every now and then, hydrogen is going to be -1. I'll give you another example of an exception here is a peroxide. So far, we've mainly been focusing on hydrogen peroxide. Again, you follow through your rules here. It's not an elemental state. It's not a simple ion. The sum has to add up to the overall charge. That's an important one. Hydrogen, we're going to give it a +1. Oxygen, give it a -2. Well, what's the problem? Well, 2 times +1 is +2. 2 times -2 is -4. 2 minus 4 gives you an overall -2, and yet this compound here is neutral. Again, because this sum rule came first, we're going to obey that rule there. And what we're going to do, the hydrogen rule came first, so we're going to keep hydrogen as +1. What would oxygen sort of need to be so that it actually is adding up to the overall charge of 0? In this case, you should be able to say to me, each oxygen would actually need to be -1. Again, that is a very strange situation, but that's how we're going to assign it. Right? It's usually pretty easy to tell whether something is oxidized or reduced if there is a change in oxidation number. If oxygen was -1 on one side and the other side is -2 or 0, something has happened. It's oxidized or reduced. More on this on the next page. That's one way of listing the rules here. Let's just go through another way of framing it. Okay, a lot of this will just be recap. It doesn't really matter which list of rules that you do. You just want to get enough practice that you can identify these charges. So, first rule here, same as mine. Oxidation state of an element is assigned 0. If I have an alkali or alkaline earth, so they're actually adding in, well, alkaline earths also typically only have 1 charge. They're adding this fact here, alkaline earth metals are typically +2, right? If it's an ionic compound and we have like calcium, well, what charge does calcium have? +2. We just mentioned here, hydrogen is almost always +1. I'd say 99% of the time it's +1. I gave you sort of the one exception. In the case of a hydride, hydrogen switches to a -1, so be it. You see that they're putting sign first in the number. Oxidation state of oxygen is almost always -2. Again, 99% of the time it's -2, except for the cases where it's a peroxide here. We just saw oxygen here being -1. Let's check this compound here. KO2. K is alkali metal +1. This is adding up to give you an overall charge of 0. Oxygen actually is kind of like having a charge. Again, sign first in the number. Each oxygen has a -½ oxidation number. Sign first in the number. Again, these aren't real charges, so it's totally okay to have the charge equivalent to sort of half an electron here, but this is a number that's going to be important for us to find oxidation reduction. They even add to it here, halogens are also almost always -1. There's many exceptions, particularly with these compounds here. Let's try a compound, let's say bromate, BrO3-, right? If you're going to say, well, halogens are -1, all these are negative, they're not going to add up to -1. So we're going to use a rule, well, oxygen is usually -2. There's 3 of them that gives -6. What does bromine have to have? So minusing the 6, it gives you -1. You should be able to say +5 there. So there's many exceptions where halogens are not -1, which is why I prefer just sort of going through this earlier list of rules. In a compound, the sum of the oxidation numbers equals the overall charge, so that was my important rule there. So for this first little bit here, they just give you a whole whack of compounds here. Go through and practice. If they don't specify exactly which element, you want to find the oxidation numbers of absolutely everything. And usually you're going to find you have rules for most of the elements here. There's always one that you just sort of algebraically solve for. So let's just do a couple here. Let's go S2F10, right? Well, if this were ionic, I know actually it's a covalent compound, but if this were ionic, the halogen would have a -1. That would be a -10. What charge does sulfur have to have? 2 of them, actually counterbalancing that to give an overcharge of 0. So that one there should be a +5. So sulfur is like having a +5 oxidation state. We can have a polyatomic. So let's say FeSO4. Well, Fe is a transition metal. I don't know the charge. Well, SO4 has a charge of -2. Fe is currently using its +2. So the transition metal, if I pretend it's ionic, that's still +2. Now I pretend even this polyatomic part is also covalent. The oxygen is -2. There's 4 of them, -8. Overall, the charge is 0. You should be able to tell me that sulfur is a +6. Sign first, then the number. Now that you know sulfur is +6, you can't just memorize sulfur in all compounds is +6. Earlier it was +5, right? So aside from this, these common elements here, alkalis, hydrogens, oxygens, which typically have these assigned charges, everything else you just need to derive for yourself. Okay. Let's do one more here. Let's go this H2SeO3, right? So the oxygen is usually -2. There's 3 of them that gives -6. The hydrogen is usually +1. There's 2 of them that gives +2. 2 minus that 6 here so far is -4. Overall, this charge is 0. So selenium here would actually have to be a +4. Again, you can use the terminology of oxidation state or oxidation number interchangeably now. Okay. Hopefully you sort of get enough practice with this that you don't actually need to write out an equation. Let's try a scarier looking compound like this H2O2P7. Basically what I'm saying is 2 of whatever hydrogen has plus 2 of whatever oxygen has plus 7 of whatever phosphorus has. That has to give for this compound here a -2 here. So when they're showing the charge here, that doesn't matter. They're not telling you this is the oxidation number, but when we go and identify the oxidation numbers, I need to make sure I do sign first and the number. So if hydrogen is usually +1, oxygen is usually -2. Oxidation state, make this note here, oxidation state is assigned per atom. So even though in my compound I actually have 2 H's, I don't necessarily know how things are bonded, 2 O's, and I have 7 phosphoruses. Should have chosen a smaller compound. Right. When I identify oxidation number, I'm saying, yeah, hydrogen is +1. Well, this is +1, and this is +1. Oxygen, well, this is -2, and this is -2. The oxidation number is always quoted per atom. What does phosphorus have to be so that it works out overall to have a -2 overall? So we have a +2 minus the 4 from the 2 oxygens here, so that gives you a -2. I add the 2 over here, so 7 phosphoruses will have to give you a 0 charge. We're going to assume that the phosphorus here is actually 0. That means each of these phosphoruses is actually 0. Okay, so phosphorus here has a 0 oxidation state here. They've given you the answers here, 32 just sort of left to right here. Okay, phosphorus, great, 0. Okay. So make sure you get a lot of practice just identifying oxidation numbers. How does that actually help us? So we're going to flip over to the next slide here. We're going to have what's referred to as a oxidation reaction or a redox reaction. A redox reaction, as I implied here, is a reaction where one species loses electrons to another, right? The other species picks up the electrons, gains the electrons, okay? These are 2 half reactions, right? One is a loss of electrons, one is a gain of electrons. That's how you can refer to these redox reactions as an electron transfer. Just like an acid-base chapter here, you have to have one guy willing to donate, one guy willing to accept. But again, the key here is it can be any number of electrons. We'll come on to balancing in a later lesson. Okay? So they're defining this for us here. What is an oxidation reaction? An oxidation reaction is a process where the species loses electrons. Okay. All of this one here, when I'm identifying who gets oxidized or who gets reduced, I'm looking at the reactant. So if, for example, I have Fe plus 2. Fe plus 2 here has already lost some electrons. It's already become a +2 charge. Let's say Fe plus 2 ends up becoming an Fe plus 3, right? Well, what's happened? Well, we're still Fe. The proton number is unchanged. But what we've done is we've actually picked up another positive charge. That means I actually had thrown away a negative. So if the electrons on the right-hand side is oxidation, you need to think about it this way. As Fe becomes Fe plus 3, it spits off an electron. This electron has now been fully ionized, is now completely loose, and it can go. So the Fe plus 2 here, we can say this Fe plus 2 has been oxidized. It turns into Fe plus 3, but that just so happens to be the product after the Fe plus 2 was oxidized. The other side of the reaction here, a reduction reaction is a chemical process where the species gains electrons. Again, usually when we talk about reduction, things are getting smaller. Why am I actually getting things? The things that I'm getting are actually negatively charged, and therefore it's actually bringing my charge down. So let's say we have hydrogen as a plus, and let's say we become hydrogen neutral. We will talk about balancing in a later lesson here, so we're going to need a balance actually for the number of atoms. 2 hydrogens is accounted for 2 hydrogens, and also for charges. I have a 2 plus overall here, I have a no charge here. This hydrogen plus actually had to have gained 2 electrons. If the electrons are on the left-hand side, we know in this case here the H plus has actually been reduced. Okay, don't say reducted. Okay, it's been reduced. Okay. Again, there's your mnemonic here. Leo the lion says grrr. Lots of electrons is oxidation. Gain of electrons is reduction. Sometimes they do another one here. Oil rig. So oxidation is loss, whereas reduction is gain. Just make sure you can remember for yourself. And in fact, that's usually the first thing that I'm going to do. If they say, oh, can you identify the species that's reduced? I'm going to just sort of reword it here. Well, reduction is a gain of electrons. They could have just asked me which one actually gains electrons. Okay. There's our mnemonic. Pretty much these redox reactions are an electron transfer. I'll let you see if you can fill out that mnemonic there. So let's have a look at an example here. So we have zinc. It's going to react with iodine. It becomes zinc ion and 2 iodide. This part here as a product would typically be written ZnI2. Right? That's going to just so happen to be soluble, so that's why it's going to be aqueous. What we want to check is whether this is an oxidation reduction. One hint for you here. You'll notice I'm starting from the elemental states, and later on it's in the compound state. Usually that's going to be an oxidation. How do I know that? Elemental states we had already assigned, well, because these elements here have 0 charge overall, I would say this zinc is 0, this iodine is 0. Sure, I have 2 iodines, both of them 0. When they're charged, they become simple ions. Zinc is now plus 2, and iodine has to now become a negative 1. So if I go from a no charge to something that is charged, probably something has happened to my number of electrons. And in fact, we can be a little bit more precise here. We're going to see whenever an oxidation number goes from 0 to a plus 2, I have gained oxidation number, right? But remember, we're talking actually electrons are actually being transferred. Have I actually gained or lost electrons for my charge to actually go up? I need to throw away negative things for my charge to go up. So in this case here, I can say that is an oxidation reaction. Oxidation implies a loss of electrons. So as the zinc on the left side becomes a Zn plus 2, it had to have lost electrons. I would expect the electrons on the right-hand side. There we go. I need to have plus 2 electrons on the right-hand side there. That is an oxidation reaction because the zinc has actually lost these 2 electrons. Again, the oxidation cannot happen unless someone is willing to pick up the electrons. The reduction here actually is a gain of electrons. It actually causes my charge to go down. So if I have an oxidation number that goes from 0 down to a negative 1, sure, I have 2 iodines that are doing that, but my charge is actually going downwards, so therefore it's actually being reduced. If I have a positive charge, it's closer to 0, or if I have a 0 charge here, I'm actually entering the negatives. In this case here, I expect my electrons to be on the left side. So what iodine here, I2, is actually being reduced when it becomes 2I minus. We've already balanced in terms of number of iodines, it's I and I. In this case here, I would need 2 electrons on the left side, and there we go, we have an electron transfer. Again, these ones here are referred to as half reactions. Our extent is short. Half reactions contain a free electron term. So I have an electron, oh no, it's loose, okay? Well, fortunately, the iodine is willing to pick it up. So if you really look at it as a sort of football transfer here, the zinc currently held 2 electrons. And basically what it does is it passes the electrons. Instead of just leaving it loose to the environment, it actually passes it to iodine, and iodine picks it up. Again, it's the reactants that we say. In this case here, zinc is put through an oxidation. Zinc is oxidized. Iodine is put through a reduction, so I2 is reduced. It happens to create Zn plus 2 and I minus, but those just happen to be the products later on. Now what we're going to do here, as we talk about balancing in a later lesson, we want to put these two together because, again, the electrons have been transferred. overall, your full equation cannot have free electrons. And what you're going to do, we're going to do a lowest common multiple step here. Well, every time zinc gets oxidized, it loses 2. The 2 electrons actually gets picked up by iodine, and therefore, when I add them up, these guys are all reactants. They should go on the left-hand side. So zinc basically passes the electrons to iodine and ends up becoming Zn plus 2 and 2i minus. This is now balanced in terms of both. So balanced for number of atoms, which we're very used to. And we're going to add to it in this section, also balanced for charge. One way of seeing that is there has to be no free electrons. No plus electrons in this final equation. If you think about that football transfer again, zinc has basically tossed the electrons over to iodine. Right? To confuse things even more here, they give you even more vocabulary. What is an oxidizing agent? An oxidizing agent, an easy way to find it is actually the one that gets reduced. Huh? That's weird. Why don't I call that the reducing agent? Turns out the oxidizing agent, by definition, it's a species that helps another oxidize. Right? Pretend you go to the store and you buy a cleaning agent. That cleaning agent, let's say it's soap or detergent, that cleaning agent helps you clean something else. It's an agent that actually allows for you to do cleaning. In this case here, we had already said the zinc is oxidized and the iodine is reduced. Who is my oxidized agent? Who actually let me oxidize? Now I know it's the zinc that actually loses electrons, the zinc actually oxidizes. Well, if iodine weren't present, the zinc would just sit around forever. If iodine weren't willing to pick up the electrons, zinc can't actually release these electrons. Because iodine is present, iodine is actually the reducing agent. Iodine is the oxidizing agent because it helps the zinc get oxidized. And in contrast here, the reducing agent is typically the species that gets oxidized. That's not the definition. I want you to define it as what does it help something do. In this case here, the reducing agent is a species that helps another reduce. So in this section, iodine itself is getting reduced. Were zinc not here, the iodine wouldn't be able to gain electrons. No one's willing to pass electrons to it. So zinc is therefore the reducing agent. It just turns out in the process of helping the iodine get reduced, usually the zinc itself ends up getting oxidized. Okay. Just based on our oxidation number sort of trend as well, we saw when our oxidation number went up, 0 to a plus 2, that was actually an oxidation. Maybe I should include that here. And oxidation is actually our oxidation number. Oxidation number increases. And we're going to see this a lot more in upcoming lessons. And reducing the reducing is oxidation number decreases. Oxidation number or oxidation state is like my charge. If my charge goes down, it's been reduced. The only reason why my charge would go down is if I actually gained electrons. Okay. Now there's one last fancy word here for you, especially when we're talking about oxidation and reduction. Sometimes we have a disproportionation reaction where we have one chemical actually doing both. This is similar to the amphiprotic stuff that we talked about in acid bases, but in this case, this guy is going to oxidize and reduce. So disproportionation is we have the same species oxidized and reduced. Let me give you an example of that here. Let's take Cu plus, and this becoming Cu plus 2 and Cu. Okay. First thing, hint, that's a disproportionation reaction while I only have one reactant. To see this a little bit better here, yes, I know the copper plus, some of it becomes copper plus 2, some of it becomes copper. What I usually do here is I just rewrite the copper, right? Still just the one chemical copper. And now I can track the changes a little bit easier. What if copper goes from a plus 1 state to a plus 2 state? What was the change? The change was I actually went up by 1 in terms of oxidation number. Because that went up by 1, this is currently copper plus being oxidized. What if other copper plus, so that's a plus 1, it ends up becoming copper elemental, that's 0. When I go from 1 to 0, my oxidation number went down by 1. Going down by 1 meaning this one here was reduced. Who passed electrons to whom? It's from the guy that was oxidized. This is the guy that currently has electrons, passes electrons over. This first guy here, upon losing electrons, its charge goes up to plus 2. The other guy picks up the electron and ends up becoming a 0 charge overall. Okay. Easy way to identify a redox reaction is typically look for an element on one side and a compound on the other side. We talked about here elements usually have assigned a charge of 0. If they're charged on the other side like an ionic compound, something has changed. Okay. So just for some practice for you, let me do one with you here. Just basic question here, who's oxidized and who's reduced? What you're going to do, I want you to find the oxidation states of absolutely everything. That's why you want to get a lot of practice. Well, iodide is a simple ion, it's -1. Iodine, both iodines are actually a 0 charge. Manganese is a simple ion, +2. This one here is the only one I need to sort of derive through. Oxygen is usually a -2. Overall is a -1 charge. There's 4 oxygens, gives you a -8. So manganese is actually a +7. So I want to track the changes here. Manganese goes from a 7 before, and now it's a 2. Its charge went down by 5. If your oxidation number goes down, it's been a reduction. For my charge to actually get closer to 0, it's because I've gained electrons. So just see if you can frame some of these terms together. So therefore, the atom that's reduced, I know it's the manganese, but I'm still going to write the entire thing. MnO4 minus is the manganese part of that compound, which means oxidation had to be the iodide, and the iodide actually lost electrons to it. You see that because things are actually compounded, I can't just look at the charges, oh, -1, and it's a little bit hard to find MnO4 is a minus, and that's +2. How is that actually reducing? Well, when you do oxidation number, you actually see, well, manganese is actually really positive charge, and its charge actually does come down. So oxidation number is just a nice tool for you to track whether things have gained or lost electrons here. If iodide goes from a -1 to a 0, its oxidation number has gone up. So therefore, plus is an oxidation. And oxidation, you know, Leo the lion is a loss of electrons. Again, we write the entire compound. It is always the reactants that are oxidized and reduced. If these reactions were reversible, if I pass the electrons the other way, sure, I could say these guys are also oxidized and reduced, but pretty much we're going to deal with one-way reactions for now. In terms of oxidizing agent, this is the thing that helps something oxidize. Well, iodine was oxidized. Were it not for permanganate, it wouldn't be able to oxidize. Again, I read out the whole compound. Permanganate is the thing that causes iodine to oxidize. And the reducing agent here, I know it's the manganese and permanganate that gets reduced. That's because iodine actually helps it reduce. Okay? So just do some practice there. Go through, find the oxidation numbers of absolutely everything. If the oxidation number stays the same, say this one here, it's a +1, hydrogen is still +1. If there's no change, no electrons have been transferred, it's only when there's one thing go up and one thing go down. Okay, so I'll leave that for you to practice, and we'll pick it up from there tomorrow. Thanks, guys.